Okay, Assalamualaikum warahmatullahi wabarakatuh and very good afternoon to all of you. So I hope all of you can access the e-learning. Okay, for those who have just registered, okay, I hope you can already access the e-learning because all the notes will be posted there. Okay, so if you have problem in accessing the e-learning portal, so please let me know. Okay, so we continue with our lecture for today. So still in chapter 1. Okay, so this is actually the introduction about the power electronic devices. Okay, so we can categorize our power electronic devices in 3 categories, which is the diode, thyristor, and the transistors. So diode is actually what we call uncontrolled device because we cannot control the device. We cannot control when this diode should turn on and when the diode should turn off. So we cannot control. It depends on the circuit, whether it is forward bias or reverse bias. While for the SCR, one part of it we can control, but the other part we cannot control. And the last one is the transistors, which is we can fully control the turn on and turn off. Okay. So this is actually the physical structure of the diode. So it can be in many shape. Okay, it can be in a stud type like this, the orange one, stud type, and also can be in the hockey puck. Okay, macam bola hockey tu, hockey ice okay, like this. Okay. And the size depends on the power rating. So if the power rating is high, so usually the size is much bigger. Okay, so this is the symbol of the diode. So I think this one you have already know because this one is already same with the diode that you learn during the electronics subject. Okay, but the difference between that diode and this diode is that this diode, what you call, is actually power diode. Okay, power diode, to differentiate between electronics used for diode used for electronics. Okay, because the power rating is different. So, but the symbol is same. So we have the anode and we have the cathode, and then this is actually the symbol of it. Okay, and this is the IV characteristic, or sometimes we call also VI characteristic. Okay, so this diode we cannot turn on, we cannot control it. Okay, when the diode is forward bias, so when it is forward bias, meaning that the anode is positive compared to cathode. So when anode is positive compared to cathode, then this diode will turn on and it will be what we call forward bias. And this is actually the characteristic. Okay, sorry, until this one. This is the characteristic when it is turned on, where you can see you have some what you call VF, the voltage drop when it is a forward bias. It depends on the material used to construct this diode. Okay, so it depends. So this is within 0.2 volt to till 3 volt. So this is the voltage drop. Okay, when the diode is turned on. Okay, so this, as mentioned before, we cannot control the diode. It depends on the circuit. So when the anode is positive compared to cathode, then it will turn on. Okay, and then when reverse, meaning that cathode is negative and anode is negative. So when this happen, so the diode will turn off automatically, and it will have this characteristic, meaning that it not allow the current to flow. Okay, as you can see, the current is remain 0 here. Okay, but at some part, at this point of value, what you call V negative VAK, this is actually the voltage, the maximum voltage blocking for this diode. Okay, so if you increase the voltage further than or higher than this limitation, so it will break the diode. Okay, so when it is break, so it will be meaning that the current can flow very large. Okay, so meaning that the diode is actually already broken. Okay, but as you can see, even though it is blocking here, so you will see that there are some what called a very small leakage current. This is very, very small, the amount which is the microampere to milliamperes. Okay, so this is considered very, very small because usually the current that flow inside this diode is around 100 amperes to 1 kiloamperes. So when considered with this leakage current, micro and milli, so it is very small. Okay. So the diode should not be operated at reverse voltage greater than what you call this one is a VR, okay? VR. So this is VR is actually the B rating for the diode. Okay, and then reverse recovery. So as mentioned before, during in our last discussion about the real practical switch where the switch requires some time, okay, to fully on or fully off. So this is what is what you call reverse recovery time. Okay, so as you can see here, this is actually during forward bias or during on. Okay, because you have a current flow I forward, IF. This one IF is actually we can consider as a I forward, and this one U is actually a VF. So this one is the voltage drop. Okay, so this is on and this is the off state. And this is actually the transition between on and off. So as you can see, it requires some finite time because from on to off. So the amount of time that requires to fully on to fully off is what we call TRR. Okay, time for reverse recovery. Okay, and this time of reverse recovery is depends on the material used to construct the diode. Okay, so this is actually example of commercial power diode that is available in the market. Okay, we can categorize it under what we call the fast recovery rectifiers. Why we call sometimes we call the diode as a fast recovery rectifier because usually this diode is used in rectifier circuit. Okay, it's normal practice, normal application is inside the rectifiers. So that's why sometimes you can find that in the market it's just saying about fast recovery rectifiers and so on. Okay, so this is the series numbers. Okay, fast recovery, and then we have ultra fast recovery. So the meaning is that fast and ultra fast is depends on, as you can see, the time TRR. So this is your TRR, time reverse recovery. Okay, so as you can see, the ultra fast recovery rectifier has a faster TRR compared to the fast recovery rectifiers. Okay, and then as you can see also, this is actually V blocking capability. What is the maximum voltage that it can block during reverse bias? Okay, and this is the current IF, I forward, the current that can the maximum current that can flow inside the diode when the diode turn on. And this one is the VF, which is the voltage drop when it is turned on. As you can see, you have a variation of voltage blocking and current forward and also voltage drop. Okay, so it depends on the materials and also depends on the applications. Some applications requires a very low losses. So instead of using this fast recovery, you need to use the Schottky diode or Schottky rectifiers, because Schottky rectifiers has a very low voltage drop. Okay, so it depends on the application. So if your application requires a very fast switching, on and off very fast. So you need to use the fast recovery or ultra fast recovery. Okay. So I hope you can understand about the V blocking, this rating, okay, forward and drop, because usually when we try to test student about the rating here, so most of the previous student, not able to answer. Okay, so that's why I emphasize more on this. So this one is a line frequencies. This is actually the diodes. Okay, so this depends on the application. So some applications requires only line frequency. So what is a line frequency? It's actually 50 hertz. Okay, so the application is for 50 hertz applications. Okay, usually this one is actually HVDC. Okay, because we know that HVDC requires AC to DC, right? AC to DC rectification before, from Thailand, for example, Thailand, 60 hertz. So you need to convert into DC, right? So usually that one is a very high power rating. So that's why we use this one. Okay, the diode that have this rating. Okay, very high current rating, very high voltage rating. But since this is a line frequency, so no need to have a very fast TRR. Okay, you can use a very slow TRR. Okay, because it is just a line frequency. Okay, and then you can also find this power diode on the fast recovery applications. Okay, and also application that inside some of the mobile power supplies. Okay, so for mobile power supply, inside that part, we usually use Schottky diodes. Schottky diode is actually very special Schottky, very special diodes. Okay. Okay, and then the next is the SemiControl, which is the Thyristor. So this symbol is also very important. Okay, so you need to know the position of the anode, cathode, and the symbol here. And then as you can see, we have a third terminal, which is this one is actually I gate the current, okay, to this terminal. So meaning that this thyristor or SCR is can be controlled because you have this gate terminal here. Okay, can be controlled. Compared to the diode, diode is uncontrollable. It depends on the circuit bias. Okay, so this is the IV or VI characteristic of the SCR. So as you can see here, the SCR is not like diode. Okay, it actually the characteristic is similar, but the difference between SCR and diode is that it will remain off until you give signal, triggering signal, which is IG here. So this triggering signal is the signal that will firing the SCR to turn on. Okay. So this is the condition. The first one, what you need to do, you need to make sure that the device is the forward, sorry, this is not forward blocking. This is forward bias. Forward bias, okay? Forward bias state, and then you give positive gate current to this terminal. Okay, so this is the two condition to turn on the SCR. The first one must be forward bias, and the second one you must give triggering signal. If this first condition is met, but you didn't give triggering signal, this triggering signal is not given, so it will remain off. Okay, so you need to have these both condition fulfill. Okay, so when it is turned on, so normally it will have some voltage drop. Sometimes we call V forward or VF between 1.5 to 3 volt. And in the reverse bias mode, so the SCR will behave like diode. So this is the condition. This is actually the characteristic of the SCR during the reverse bias, which is same like a diode. Okay. So that's why the SCR is called semi-control, because we can control the device to turn on by delaying the signals. Okay, the IG signal you can delay, even though it is forward bias, but until you give the triggering signal, so it will remain off. Okay, so we can control the timing when this diode should turn on by delaying this signal. Okay, but to turn off this SCR, you cannot give control signal. Okay, to turn off, what you need to do is to give is actually uncontrollable. Okay, you need to have the circuit to be in reverse bias. So that's why the SCR is semi-control. We can control turn on, but we cannot control turn off. Okay, because the power electronics only two state, on and off. Okay, so the diode is uncontrollable. The SCR is semi-control. Okay, and then this one I think you can. Okay, this is the Thyristor conduction. This one is actually what we have already explained. I have already explained. Okay, and then this is the type of Thyristor. We have the phase control, inverter grade. This is actually depends on the applications. Okay, we have phase control. So phase control usually very slow frequency. So usually for very slow frequency, usually the rating is can up to very high rating voltage and current. Okay, and then we have inverter grade. So this one is used for in the inverter systems, light activated, and we have the triac, which is a very special one. We have this one SCR, two SCR combined together, and this triac you usually find in the juice maker, blenders, vacuum, and also the um, washing machine. Okay, because sometimes the washing machine will rotate clockwise, sometimes the washing machine will rotate anti-clockwise. Okay, so we categorize this Thyristor in terms of its applications. Okay, this is the most interesting part, which is the controllable switch, which is the main power horse or the main component in the power electronics. So usually compared to the diode and the SCR, so transistors is actually we can consider as the most used device in power electronic circuits, because it can control. Okay, we can control when the device should turn on, okay, and off. Okay, so so it is operated in saturation and cut off. Okay, and no linear region operation is allowed. Okay, and the transistor that we will discuss late in this class is the bipolar junction transistor BJT, the MOSFET, IGBT, and so on. And then we have emerging new devices, what we call GCT and MCT. But usually for power electronics, due to the cost, okay, because actually this MOSFET, this MCT and GCT is very, very expensive. So what usually in our research in UTM, we usually just use MOSFET or IGBT. Okay, because they are cheap compared to others transistors. Okay, let's begin on the BJT. So this one is the first transistors invented in 1948. Okay, and this is the symbol. So you have, symbol tak bertukar. Memang it's actually remain the same. So you have collectors, you have emitter, and you have base. Okay, so this part is what we call control. Okay, it's a control part, and at this part is actually the output. That okay, output part. So usually for the transistors, what we do is actually we have a VDC maybe 100 volts. Okay. This is your BJT. Okay. So this is your base. As you can see, this base is actually come from your microprocessor. Okay, the signals come from your microprocessor, and this BJT will connect. Okay, this is your collector, and this is your emitter. This collector and emitter will be connected directly to the power circuit. Okay, maybe you have a resistor here. Okay, so this is your IC. This is also your IC. Okay, and this is the VCE. Okay, so this is actually the typical diagram to show you how the connection is. So usually the base is the control, which is come from the microprocessor, the signals. So microprocessor, you know, is actually electronic part. Okay, the voltage is actually VCC, which is maybe 5 positive minus 5 or positive minus 12 volt. Okay, so very very small voltage, and current is also very small. So this is for control input, while the collector and emitter is actually the terminal that connected to the power circuit. Okay, so this is the IV or VI characteristic. Should be IV, should be. Okay, IV, because I versus V, current versus V. So this is IV. Okay, so why IC and VCE? Because this is the output, IC and VCE. So we want to see the correlation between IC and VCE when we have variation of IB. Okay, so as you can see, this is the characteristic when you have IB1. This is the second characteristic, okay, I for IB value number 2 and so on. Okay, and in transistor, just to recall back, so we can divide the transistor region in 3 regions. Okay, so this is what the region that you have learned during the electronic course. This is actually what we call active, or sometimes we call linear region. This is where in electronics, they say that you need to operate your transistor in this region, because in this region is where your transistor will operate as an amplifier, right? But in power electronics, we will not operate this at active or linear region. Okay, we only operate at only 2 region, which is this one, what we call on or saturation region, which is when you operate it at saturation region, meaning that the transistor is on, and the second region here, which is what we call cut off region, okay, which is state off. So on and off. So the switch is either on or either it is off. Okay, we will not operate our transistors at this active or linear region here, because this is amplifier. Okay, so when you increase the IB, you will have a different IC. Okay, so this is where you use that for amplify the signals. But in power electronics, we only use transistor as a switch, on or off. Okay, and the transistor can be either PNP or NPN. And the rating, okay, the voltage rating, just to highlight, okay, this VCE 1000 volt is not voltage forward. It's not voltage drop across the VCE during on. This rating is actually, what is it? This is not V forward, okay? This is the rating during blocking or during V off. During when it is off, what is the highest voltage that it can block. Okay. And then the rating of the current is usually the current forward. The current during turn on. When this transistor is on, what is the maximum current that is allowed to flow inside the transistor? Because every transistor, there's some limitation because different materials used. Okay, so I hope you can understand about the rating here. The voltage rating usually in the powertronics is referring to the blocking voltage, while the current rating is usually referred to the current flow during on state. Okay. You can interrupt me if you have some question, okay?
Excuse me, doctor.
Yeah.
Yeah, when we operate the transistor in the saturation and the cutoff region, it's gonna act as a switch, or
Sorry?
if you operate the transistor in the saturation and the cutoff regions, it's gonna act as a switch.
Yes, yes. On and off. Yes.
Okay.
Yeah. So in powertronic, only saturation or cut off. Saturation meaning that it is on, the current will flow. Okay, you will see that the current will flow. Okay, the current IC will flow here. And during off, you will see that the current is zero, meaning that it is off condition. But the voltage blocking, okay, it will be here, depending on the circuit. Okay, and then this is the some limitation and also the advantage of the BJT. So the switching, okay, on and off, okay, the capability is very, very low. You can only operate it up to 5 kilohertz, very, very slow, okay. And the voltage during the voltage drop during on state is very high, 2 to 3 volt, very high. Okay, and then in terms of the gain, okay, the current gain, because we know that IC is equals to beta IB. Okay, because this one is related to this one. Okay, it's very, very low, so you need some Darlington pairs to increase the beta. Okay, to get the reasonable IC here. Okay, so reasonable IC is not integrated circuit, it's actually I, small letter IC. Okay. So to get IC, reasonable IC up to 400 amps, so you need to have a higher beta. But usually for BJT, the beta is very, very small. Okay. And then very expensive and complex base gate driver circuit. So what is mean by driver circuit? Actually, I will explain this at the after this. Actually, the driver circuit is actually we have a computer which is your micro P, which with all the algorithm is there. Okay, and then you have this BJT, right? BJT. So to match the microprocessor and BJT, you have some electronic circuit, what you call gate driver. Okay, so gate driver is actually an electronic circuit that interface between the microprocessor and also the transistors. So I just want you to show you, because I have only received I have ordered a gate driver and only received it yesterday. So maybe I can show you. This is actually the gate driver. Okay, so this is an electronic circuit, very, very small. Okay, electronic circuits. Okay, this is the gate driver that. So for the BJT, this gate driver is very, very complicated to design. So that's why it is not very popular. Okay, so that is the disadvantage of BJT, because very complex gate driver. Okay, so this is the Darlington pair. So this is actually what you want to do, what we should do to increase the IC, okay, the value of the current that can flow inside the collector. We need to use a Darlington pair. Okay. The second transistor is the MOSFET or metal oxide silicon field effect transistors. I think in electronics, have you learned about the MOSFET? I think maybe JFET, right? JFET, if not mistaken, because during my electronics subject, we have been taught about JFET. But I don't know in this current syllabus whether it's still JFET or MOSFET. Okay, never mind. So this is a MOSFET. This is the symbol. So you need to, I think you need to remember this symbol. So you have a drain, you have source, and you have gate terminal. Okay, and then so in that, this is actually the input part, which is the control signal come from here, and then this is actually the output part. Same like BJT, so the output will be connected to the power circuit, while this gate terminal will be connected through the gate driver from the microprocessor. Okay, so this is the IV characteristic. Okay, at the output side, so ID versus VDS. Okay, but compared to the BJT is actually use IB, right? IB as a controller. But right now in this MOSFET, it uses voltage VGS to control the characteristic of this MOSFET. Okay, so same with the BJT, we have 3 region. We have this one is what we call saturation or on, and this region is same, which is the off. Okay, and this region is what we call active region. So but active, we will not use this. Okay, we only use it, the MOSFET, whether on and off. And for the MOSFET, we have 2 type, which is N channel and also P channel. Okay, so this one you can see that the voltage blocking is not very high. Okay, this is the V blocking. It's not very high. Okay, 500 volt maximum it can withstand. While and the current also, this is IDS. IDS is the I forward or I during turn on. So the maximum current that can flow inside the MOSFET is also very not very high. Okay, less than 300. Maximum is 300. So that's why MOSFET is not suitable for high voltage and high current application, because most of the MOSFET available in the market, the maximum is 500 volt withstand. Okay, the blocking voltage, and the current is also not very high. But the advantage of MOSFET is that it can switch very high. The frequency switching more than 100 kilohertz. There are no other transistors that can be switched at this very high switching. Okay, so MOSFET is the king in terms of the switching. Okay, but the voltage and current is very small. That is the limitations lah. And then another advantage, okay, apart from the high switching frequency, another advantage is that the gate drive is very simple, because to turn on the device on, you just need to produce VGS equals to 15 volt, and to turn off the VGS, you need to only give VGS equal to 0. Very simple. So the gate driver circuit that I have already showed you is the gate driver for MOSFET. Okay, for MOSFET. So very simple. So this is very popular, but only for low power applications. Okay. So but the most disadvantages The first one is because of the low power rating. Okay, the MOSFET cannot have a very high power rating. Another disadvantage is that during turn on, the internal, okay, the internal dynamic resistance, which is RDS, the internal, we have some internal resistance here, which is RDS. This is RDS is actually the values that because of the material use, okay, in the MOSFET, RDS, okay. RDS on, meaning that during the on state, the resistor value is very, very high. So that's why when you have internal resistance very high, meaning that during on state, the losses is very, very high. Okay, so that is the second limitation of the MOSFET. Okay, so this is the example of a commercial power MOSFET. So as usual, this one, if you come to see that this is rated maximum, is this one is the V blocking. The capability of the device to block the voltage during off state. And this one is the I on, okay, or I forward during during on state. And this one is R on. This one is referring to the RDS on. RDS on. Okay, only MOSFET data sheet has this RDS on data here, because this is very crucial in selecting which MOSFET is suitable for your applications. Okay. And okay, lastly is the IGBT. Okay. So to summarize the IGBT is actually you have BJT, right? We have already BJT, and you have MOSFET. Okay. So the BJT and MOSFET is combined together or married together, and then you will deliver a son or daughter, which is IGBT. Okay, macam apa? LGBT IGBT or LGBT. Nasib baik it's not LGBT. It's lesbian, gay, bisexual, apa? I pun tak tahu nanti apa ni, transsexual. It's look like macam tu lah. Every time if I want to make joke, so usually actually by doing that, the student will actually memorize more. Okay, easy to memorize, because actually the IGBT is actually a combination of the advantage from BJT and the advantage of MOSFET. So combined together, so this one you will have a much better transistors. Okay, much better transistors. So as you can see, the symbol is also like a combination of BJT and also MOSFET. So the symbol is like a BJT, but the terminal name is like a MOSFET. So you have collector. Okay. Okay, so kalau in the MOSFET, this one is what called drain, right? But in the IGBT is called collector. And then this emitter, okay, like a BJT, but the terminal gate in terms instead of using B, it use the MOSFET terminal name, which is gate. Okay, so the control part is controlled by the VGE. So the value of VGE will determine the on and off. Okay, so meaning that VGE 15, if you give 15 volt, then the IGBT will turn on, and if you give a VGE 0, so it will turn off. This is the IV characteristic, IC versus VCE. Okay, so whether it is on or whether it is off. Okay, so this is actually the behavior of the IGBT. So meaning that you have, as you can see, The gate driver is very, very simple. Just very simple to turn on. Just you need to have a 15 volt to turn off 0. So it looks like a MOSFET. MOSFET punya advantage. Okay. And then there are other advantage lah from the IGBT. You can read this from the slide. Okay. And as you can see also here, the rating is can be, I think this one can be a very, very high rating lah. Okay, unlike MOSFET, MOSFET is very low power rating, but this IGBT is actually use a BJT characteristic. Okay, so in terms of the rating, voltage and current, it can up to 3.3 kilovolt, and current it can up to 1.2 kilo amperes. And the switching frequency is also very, very high compared to BJT low, but the MOSFET is also high. So actually this IGBT combine the BJT and also MOSFET advantage. So usually in the middle. So the rating is actually in the middle. Okay, not very fast, not very low. Okay, so this is actually the example of the commercial IGBTs. So you can, this is the number series here. Okay, so GTO, I think I can skip this one because GTO is actually it's like the symbol is like SCR, but the different, the characteristic also same. Okay, but the only difference between GTO and also SCR is actually it is controllable. So this is actually transistors. Okay, still transistor, but the name is actually gate turn off thyristor, but it is actually a transistors. Okay, the symbol is like a SER. Only the difference is, as you can see, we have here two-way. Okay, two-way of gate signal here, meaning that you can turn on and turn off this GTO. Okay, so this GTO usually have a very high voltage and high current rating. Okay, but the frequency switching is low. Is low. Usually like that. When you have a device that have this high voltage and high current rating, usually the switching is not very, very fast. Okay, so there is a trade-off. So when you have switching is very, very high, usually the power rating is very, very low. For example, is the MOSFET. Okay, switching is very high, but it not capable to handle high voltage and high current. So for this gate GTO, you can handle high voltage and high current, but usually the switching is very, very slow. Okay, so as you can see, you have a very high current. The capability, the rating, very high current and voltage, but the frequency, as you can see, is very, very slow, less than 2 kilohertz. Okay, and then you have this one IGCT. So same with the GTO, the IGCT also it can up to very high power rating, but the frequency is very, very slow, as you can see here. Okay, the rating. Okay, when you have high rating, power, voltage and current, but the frequency should usually very, very slow. Okay, you have the MCTs and so on. Okay, so this is the switch idealized characteristic. So this is what called ideal. Ideal meaning that we ignore the voltage drop and so on. So for the diode, so this is IV characteristic for the diode. As you can see, when it is turned on, it will turn on, the current will flow very high current, but the voltage drop is 0. And when it is reverse bias, so it will remain off. Okay, the current is 0, but there is some voltage blocking here. Okay, that is for the diode. And this is for the SCR. Okay, so the SCR, as you can see here, we have forward blocking, meaning that if you didn't give you IG, okay, the SCR is like this. This one is anode, this one is cathode. So if IG is 0, even though it is a positive forward bias, it will remain off. It will remain off. But when you give IG 1 or a value, so it will turn on. Okay, so that's why we have here, turn on. So it depends on the IG. There is a two condition. The first one, the forward, the SCR must be forward bias. Okay, and the second condition, you must give a triggering signal. So when you give triggering signal, both conditions are met, then it is on. From off, it's going to turn on. And this is the reverse blocking, same like diode. So for the SCR, you have this characteristic like this. Okay. Same with the GTO. So GTO is actually same characteristic with the SCR. The only difference with the GTO, the GTO is like this. We have already see. We have two, right? The GTO. So this is anode and cathode. We have this one. You have two way of arrow, meaning that it can either turn on and turn off, whether on to off or on to on. And this is for the BJT. So the transistors, so it is fully controlled. So like a GTOs, so GTOs is like a SCR, dia punya characteristic. For this BJT is the transistors. So BJT and MOSFET, as you can see, is same. Okay. The IGBT, I think, sorry, the IGBT, sorry, this one I think is incorrect. So the IGBT is also same. You have the same like transistors. The only difference is that you have this one is IC, this one is your VCE, right? The characteristic is same with the transistors. But this one is IC versus VCE. Okay. So BJT IC versus VCE. For the MOSFET is I drain versus VDS. Okay. So this is the switch idealized characteristic. Oh, saya rasa macam sesak nafas sikit. Banyak sangat bercakap. Talk a lot. So I think this is the effect of the COVID because previously, I think 2 weeks ago, I have been infected with the COVID. Still not fully recovered, even though tested negative, but I think it's not fully recovered. What I call this one a long COVID effect, right? Okay, any questions? Yeah, actually, but the weird thing is that I think 1 month ago, my family got infected positive. So all my family member, my wife and my children are positive. And then since all positive, then I think we just quarantine inside the house. Okay, so meaning that I slept with them in the same bed and so on because I assume that I will also be positive because because all of my family were positive, but somehow even though they are positive, I'm still negative until they negative. Until 7 days after they check, they negative, I still negative. Okay, but and then after they negative, and then a few weeks after that, 2 weeks, I think 2 weeks after that, then I got infected, which is I don't know where and how I got infected. Okay, and the weird thing is also for 13 days, 14 days or 13 days or 14 days, at the date of 14 and 13, I still positive. Yeah, with the day 13 for the day of 13, I still positive. Okay, and then only day 14 I got negative results. So it's quite weird because all my family members they turn to negative until day 4, then then they are fully negative. But I need a very longer time to recover. Okay, day of 14 then I negative. So for almost 2 weeks my result is positive. So it depends on the body, right? So itulah. Okay, so this is the classifications lah, based on the power rating and the frequency switching. So as you can see, MOSFET is actually uh, MOSFET is a very okay for the application that lower than 10 kilowatts. Okay, 10 kilowatts, but it can be applied at very high switching frequency. So okay, the application. So this is the limitation for MOSFET. Okay, and for the IGBT is actually at the middle. Okay, at the middle. So you can at the middle power. So you can up to 1 megawatts, and the frequency switching may be up to 100 kilohertz. So this is actually the IGBT suitable application. And you go up again, you go up to high power. So this is where the Thyristor and GTO and also IGCT applications. Okay, so usually for the high power but low switching frequency, the Thyristor and GTO is the most suitable. Okay, and there is no device yet that can able to handle high power and also able to switch at very high switching frequency. Right now, that component or that power semiconductor is still not available under research. Okay. So this one also, and then as you can see, okay, this is the applications. So usually for the Thyristor is mostly suitable for the HVDCs, GTO for the train, okay, UPS and so on. And then for the MOSFET is mostly suitable for the microwave oven, power supply for audios, electric vehicles. So mostly they are use MOSFETs and so on. So this is the type of application that related to the devices. Penat juga bercakap ni online.
Excuse me, doctor.
Yeah,
For the previous slide, for the graph of the power and the
frequency.
yeah, why does the power degrade after 100 kilohertz for like different devices?
Oh,
For example,
okay, okay,
MOSFETs, yeah.
okay. So this is actually not degraded. It's actually the classifications of the devices. Okay, right now, there is no such device that can actually have both capability, which is high power and high switching capability. There is no such device. So here X. So usually, the device that for high power, usually they not able to have high switching frequency. Okay, which is we have already explained this in the first introduction chapter. This one, right? Switching speed and power. So as you can see, this is the limitation. There is no such device that can actually able to meet both high power and high switching frequency. There is no such device. We limit here because of the materials. Okay, our right now our technology. Okay, The device that can handle high power, usually they will have limitation of in terms of the frequency. So they cannot switch at very high switching frequency. Okay, which is sometimes, for example, the diode, okay, SCR and so on. Okay, and there are also a device that can up to very switching frequency, but for example MOSFET, but because of that, okay, the material that used for to design the MOSFET, okay, it cannot have the capability of handling high power. Okay, this is the limitation right now because of the technology. The materials technology is still not yet. This is the boundary. You cannot have you cannot have the transistors or power semiconductors that has both, that can fulfill both high power and high frequency. There is no such device right now available in the market. Maybe 10 years, maybe after this 20 years, because of we have a new technology comes, then maybe we can have such device that can handle high power and high frequency. Okay, I hope I have answered your question. Okay, there is no such device. So if you want to have usually high power, so usually the limitation is that it cannot be switched at high frequency. Okay, if you want to have high frequency, the limitation is that it cannot handle high power. This is not what we call this is actually due to our limitation, our technology limitation right now. This is the limitation. We cannot have this. Still, we cannot have this because right now the research in the materials, we haven't found yet what is the best suitable material used to manufacture semiconductors that can able to handle high power and able to have high switching frequency capability. Okay, so that's why sometimes usually we use medium one, which IGBT. Okay, IGBT is a medium, meaning that it can handle medium power and also it can handle frequency, medium frequency. But it depends on the application. Okay, it depends on the application. As I mentioned in this graph. Okay, depends on the application. Usually for the HVDC, yes, for HVDC, usually we didn't switch at very high switching frequency. It's only 50 hertz or 60 hertz. Okay, but and usually the voltage current rating is very high, so no need to have to use MOSFET. Okay, maybe you use a Thyristor is good enough. Okay. Okay, and then this one comparison. Okay, the further development in power device. So as mentioned before, it depends on the technology, the material technology. Right now, it's actually beyond power electronics. Okay, this one is actually beyond power electronics. This is research materials, research in materials, to combine some materials to get better semiconductors. So right now, we have a new technology, which is what we combine a silicon with a carbide. We call the silicon carbide, a new technology, materials. Okay, new technology of the materials, and the other one is the gallium nitride, which is GaN. So that's why sometimes maybe in the market, like Shopee online, okay, you have a charger, what I call GaN charger, GAN GaN charger, very fast and very very fast charging because it can produce high current to the battery, very high current. Because so actually the rate of the charging of your handphone is not depends on the voltage. It depends on the current, whether the battery of your handphone can can absorb the high current or not at a very short period of time. Okay, so that's why sometimes your handphone, it depends of your handphone, your charger controller, whether and your battery, whether it can absorb that current or not. Okay, so some handphone, even though you buy a quick charger, which is the gun charger, it cannot. It's actually can charge it very quick, but your battery will be shortened. The life of your battery will be shortened because the battery is not optimized for quick charger to absorb high current during the charging mode. Okay, so you if you want to have that capability, you should buy handphone that already come with the capability of have this what you call, it can actually absorb high current. So actually the quick charger is actually the current is very high during the charging period. So whether your battery is capable to absorb that current or not, it depends on your charger system inside your telephone, not on your charger, wall charger. It actually depends on your charger system inside your telephone. So that's why some telephone is very high price, because it need to have a very complex controller to charge the battery. Okay. So gallium nitride is a charge. Right now, if you go for the gadget shop and so on, so you will see this what you call GAN, gun charger. So the gun charger mean that it can, that semiconductors actually can process, okay, can rectify or can process the very high current. Okay. So this is actually the technology materials that we have already found. Actually, this one have already been found 10 years ago. 10 years ago. Until, because you know, when you found the technology, 10 years, then to get it into the market for the consumer usage is usually take around 10 to 20 years. Okay, because you need to have that system to be very stable uh, to get that inside the market. Okay, so this one is actually 10 years ago. The finding of this silicon carbide and also gallium nitride. So this is actually the classifications. So where what we call silicon carbide and yttrium. So this is the silicon. So this is actually the conventional. Okay, the conventional silicon, where from here we can see that we have VJT, MOSFET, IGBT, and so on. But this one we have a new material use. So as you can see, we may have a very high power, maybe high power and high switching frequency capability. Okay, so as you can see, this is the limitation right now, the silicon. By using the silicon carbide and gallium nitride, the boundary can be increased. Okay, so meaning that the capability of handling high power and also high frequency switching can be increased. Okay, I think that's all. Okay, so can we take a break about 10 minutes before we proceed with part 3? Okay, so 10 minutes, okay? Okay, so right now it's 12:06. So we will start at 12:16. Okay, 12:16. Okay, thank you very much. So we meet again at 12:16. Okay, Assalamualaikum. Okay, I think we can start on the part 3, which is the gate drive circuit. Okay, so which is actually the circuit that I have already showed to you. So this gate drive circuit is a very important. Okay, so what is a gate drive? So a circuit that are constructed to turn on and off the power device. Okay, and it provides an interface between the control signals, which is the small signal electronics, and power electronics. So sometimes it calls driver circuits, and sometimes it calls gate drivers. So actually gate driver and driver circuit is actually referring to the same circuit. So this is the block diagram that shows the position of the driver circuit or gate drive. Okay, it is actually an interface or located at the between the control circuit and the power circuit. Okay, so I hope you can see right now. So I'm showing in the camera right now. This is the control circuit, which is a microprocessor or microcontroller, and then this one is Uno. Okay, Uno, Adreno Uno. Okay, Adreno Uno, which is this is one of what you call a microprocessor or microcontroller. This is where I think you have already know how to use this Adreno Uno. Okay, this one you plug in using USB or any connection, and then you do all the programming here inside here. Okay, and you know that the output signals from this Adreno Uno is actually 5 volt, if not mistaken, is either 5 volt or 0. Okay, 5 volt. Okay, okay. I hope this one is Adreno Uno. This is actually what you call control circuit. Okay, so I turn on my camera right now, so you can see this the control circuit. This is actually my microprocessor. So the output from this microprocessor is actually a signal output. Okay, a digital signals. So 5 or 0 and so 5 volt and 0 volt. Okay. Okay. So if you are using MOSFET, for example, MOSFET. This is the MOSFET. Okay. This is the power circuit. MOSFET. This is 1, 2, 3, 4. 4 MOSFET transistors. Okay. What is the requirement to turn on the MOSFET? What is the requirement to turn on the MOSFET? What is the requirement?
I apply current at base.
MOSFET.
High frequency.
No. What is the requirement to turn on and turn off the MOSFET?
Voltage at VGS.
Yes, voltage at VGS must be how many voltage? What is the value?
15.
Yes, 15 volt to turn on. And to turn off must be 0, right?
Yes.
Okay. So right now, the output from the Uno is 5 volt. The output signal from the Uno is 5 volt. So how to turn on the MOSFET? The MOSFET requires 15 volt. The signal, right? To turn on the signal, the control signal must be 15 volt. But right now, the output from the Arduino Uno is 5 volt. So this is where you need gate driver. The gate driver will increase the voltage. Okay, so from 5 to 15 volt. So that is the purpose of gate driver. So the gate driver is the interface between the microcontroller or your Arduino Uno and power circuit. Okay. Sorry. So the first, there are two functions of the gate driver. The first one, to amplify the control signal to the level required to drive the power switch. Okay, for example, you have MOSFET 15 volt. Okay, so this driver circuit will amplify that signal from the microcontroller 5 to 15 volt. Okay, so that the MOSFET can be turned on. The second one is to provide electrical isolation between the power switch and the microcontroller. Okay, so actually microcontroller, you actually plug that microcontroller to the computer, right? To the computer by using USB or any parallel micro connection and so on. And your computer is actually maybe priced around maybe 5,000 ringgit. Okay, so right now, if there is no protection between the power circuit and your microcontroller, Okay, so anything that happened to the power circuit, for example, maybe short circuit and so on, so that current, leakage current or short circuit current will go back through your computer and it will damage your computer. So we don't want it to be happen like that. Okay, usually computer is around 5,000 ringgit. Your power circuit is around maybe 100 ringgit. You can develop that power circuit around 100 ringgit. So very cheap power circuit, okay? But your computer is 1,000 ringgit. So we want to protect your computer. So that's why what we need here, gate driver. So the second function of the gate driver is the isolation. So how to do the isolation? As you can see here, this is the transformer, high frequency transformer. So you may have already learned that transformer is used for isolation, electrical isolation between the input and output. So in this gate drive, we use here the high frequency transformer to isolate between the input signal and the output signal. Okay, so there are two functions of gate driver: amplifiers and also isolation. Okay. So this is actually the circuit how to amplify. Okay, so this is actually I've already shown you. So I think we can skip this one. Okay, so this is some description. I think no need to explain lah. Okay, and then this is the isolation that I talk about. Okay, using the what called the high frequency transformer, which is I have already shown you. So the transformer will provide the isolation. Rather than using the transformer, you can also use optocoupler, which is also an isolator. Okay, so I hope you can see this. This is another PCB, I think inverter circuit. That this one is actually integrated. We have the power circuit and also gate driver. So, but this one, as you can see, this is the gate driver. This part, but this one is used cheap, which is optocoupler. Okay, we use an what you call the some optocoupler chip here. Okay, to isolate between the input and output. So this is optocoupler. You use a integrated chip. This one we use transformer. Okay, for isolation. So for isolation we have two kind of isolation. Oh, dah habis dah. Okay, so next we go for chapter 4. Oh, yeah, chapter 1, part 4. Okay, I think this one I will go about the power losses lah. I think very fast this one. This one actually we will go deeper on our next class lah. Okay, but I want to show you something about the heatsink. Okay, just to show you about heatsink. So this is actually when you turn on and off the power switch on and off and on and off. So actually your transistor will become very hot. Okay, your transistor will be very hot, and for a device, okay, there is some optimal condition so that the device can perform very good. Okay, so for example, this transistor use maybe around 60 degrees. Okay, so the optimum temperature for operating is 60 degrees. So you need to always maintain that temperature to 60 degrees. On how to maintain that temperature to 60 degrees. Okay, so the temperature, the heat generated from the transistors need to be dissipated to the environment. Okay, so that's why we have what we call the best, or not the best lah, it's actually the cheapest technique is by using heatsink. So as you can see, this is the MOSFET here, attached or glued to the heatsink. Okay, so all the heat will be transferred to the heatsink, and this heatsink will dissipate all the heat to the surrounding. Okay, and this is also another circuit. This is also inverter circuit, as you can see. So different kind of heat sink. Okay, so different kind of heat sink. So this is much more steady, much more sturdy compared to this one. So actually, the size of the heat sink will actually determine the compactness of your system. So that's why there is also research on how there is a calculation on how to determine the suitable heatsink size. Okay, so that your temperature will remain optimum. The temperature of the transistor will remain optimum. So this is, as you can see, this is actually your transistor is very small, but the heatsink take the most of the part of the PCB. Okay, and it is very heavy because of the heatsink. And this is a capacitor. Okay, just capacitor just for filter out the voltage so that the input voltage is a pure DC voltage. Okay, so this is actually the heatsink, and then we have another method which is a very complicated method. We have, for example, we have direct water cool, okay? Like your car, your vehicle engine. So your engine will become hot. So how to actually cool down your engine is actually by using radiator, right? You have the radiator and so on. So to cool down the engine temperature. So that is actually higher cost, okay? So for power electronics, usually what we do is just use the heatsink. Okay? Okay, I think that's all. Because I also didn't tak sangka pula yang tu dia punya slide is very short. Okay. But I think we will be more on the switching losses, okay, on our next class. This is also very crucial. The switching losses, and then we will talk about snubbers, okay? Snubbers, because snubbers, as you can see, we have this overshoot and so on, how to remove this overshoot. And lastly is about the cooling effect. Okay, so there's three elements for our next lecture. And then, so next week, we will move on the second chapter, which is the rectifier circuit. And that chapter, we start all the analysis, okay, all the calculation, analysis, and so on. Okay, I think that's all. Thank you very much. Any question?
Excuse me, doctor.
Yeah.
Video recording video, it will be found in the e-learning.
The video I have already insert. I will actually usually I will upload in my YouTube channel. My YouTube channel in the WhatsApp group. If you go to the WhatsApp group and then inside WhatsApp group there is a description. Inside that description there will be the yeah.
The link, yeah.
The link. This is my YouTube channel.
Okay.
Okay.
Okay, doctor. Thank you.
Okay. So all my videos will be uploaded there. Okay, I think that's all from me. So we meet again on Thursday class.
Thank you,
Okay.
Doctor.
Okay. Assalamualaikum. Yeah.
Thank you.
Salam.
Thank you, Doctor.
Okay.